Okay, so let's work this problem. So what it asks for is you've got this cord ABC stretched around a frictionless pulley, and you have a second cord from B to D. The maximum load that this system can support is 100 pounds. So we need to, that's the maximum load in the cable. Okay? So we need to find what is the maximum load in the crate and what angle the system will be at. Okay? So that's really our two unknowns. So let's get started. We're going to know the tension in the cable. We're going to assume that it's going to be at the limit. So let's go ahead and draw a free body diagram at B. So here's our free body diagram, and we're going to draw that at B. The first part is easy. There's our particle. And then we'll have the weight of the, I'll idealize this a little bit, so I'll have the weight of the, maybe I'll do this. I'll just include the pulley just to make it look a little easier. So I'll have the crate weight hanging down. I'll call that W. And then over here off to the side, the other pulley going in this direction. What should that also be? Over a frictionless pulley, it should be W also. And we know it has components in the 5, 12, and we know that's going to be 13. And coming off the center of this will be the tension in cable BD, and we're interested in this angle theta. So I think that's a pretty complete free body diagram. Okay, so let's start by assuming to the right is positive. Let's sum forces in the x direction and make sure they're in equilibrium, equal to 0. Let's do that. So what are our x components in this system? Starting with the weight, what's the x component of that? Well, that'd be the horizontal piece, that'd be 5/13, right? So 5/13 of W. And then the x component of this is going to be what? It's going to be negative. Tension in BD times cosine theta. Everybody see that? Now, what's the maximum load in the cable? Well, we'll come back to that. Let's just go ahead and write it. So let's sum forces in the y direction. What do we have? We've got W acting down. We've got the y component of the other side, which is what? Say again? Right, 12 over 13, W. And then we have the vertical component of TB, or TBD, and that's acting up. So that will be plus that value sine. Did I leave anything out? Now it looks like at first glance I have two equations and three unknowns: the weight, the tension, and the angle. However, I know that the cords can only go 100 pounds. So that means I know the tension. So let's assume right now that the tension VV is equal to 100 pounds. We can do that, right? We'll let it go to the max. Now with that, I have two equations and two unknowns. I should be able to solve for W, and I should be able to solve for theta. Now, what if W comes out to be greater than 100? Right? That means that my assumption for letting VV go to max was incorrect. So that means that the maximum weight would be 100, and I have to try it again to find the other table value. You guys see that? So let's just start with this first. Let's see if this is going to work. We'll check it when we're done. So I plug TB back into here, and I plug TB back into here. I have two equations and two unknowns. So I'll rewrite those. So the sum of the forces in the x direction will now be 5/13 W minus 100 cosine theta. And my y equations, some forces in the y direction, I guess I'll lump these together, right? -1 minus 13. What's that? That's 25/13. And that'll be plus 100 sine theta. Do you see that? How can I solve those two equations? Let's just call this equation 1, equation 2. Well, this is another thing you can do with equations. I'm going to take one equation and let's see, what am I going to do? Well, let's go ahead and rewrite them. So I'll do this. 5/13 W is equal to 100 cosine theta. That's equation 1. And then we've got our minus 25/13 W. Oops. Put that to the other side. Positive is equal to 100 sine theta. Okay, now it might be a little clearer. Everybody see that? I can actually now divide equation 2 by equation 1. So if I took equation 2 and divided it by equation 1, what would I get? So the 100 could cancel, right? So I'd have 100 sine theta divided by 100 cosine theta, which is what? That's just tangent theta, right? Okay. So now the other side I divide, right? So what is that? Is it just 5W? Well, the W's cancel. So it's just 5. Right? So I should be able to solve for theta. What's theta? What's the arctangent of 5? .69. Everybody see that? There's other ways to solve this. I'm just up here winging it. So now if I have theta, I can plug it back into one of these equations and solve for W. So let's just pick one. Let's pick the first equation. So it looks like then W, if I solve for W, it would be 13 over 5 times 100 cosine theta. So take the cosine of that, multiply all of that, what do you get for the weight? So the cosine of 78.69 times 100. Yeah. Times 13 divided by 5. What do you get? 50. Yeah, 50, okay, that's good enough. 51. So, is that good for us? Yeah, it's less than 100, right? Which was the max. So by assuming that the maximum value was in one table, and I solved for the value in the other table, it was okay. Now, if this had come out to be, let's say, 101 in groups, what would you do? Right, you'd have to go back and assume W was at the max, and then solve for CVV. Any questions about that? Oh. I looked at the problem beforehand. It kind of made sense to me also because with two cables, I just thought, well, you know, they're probably going to have, you know, this cable really is going to be nearly twice these two. Because if you look, if they were all vertical, then if this were 100 pounds and this were 100 pounds, this would have to be 200 pounds. So it made some sense to maybe think that this was the max. Now, whether you saw that or not, I mean, that's good if you see that, it saves you time, but mathematically, you would have come down here and found that, oops, I chose wrong. That means you just have to work the problem again. I guess but given enough time, it wouldn't have been an issue. Any other questions about this one?